Let's go ahead and resume recording. So now we're talking about moving. Now before we talked about velocity, talked about acceleration, and talked about position. Now it's time to start talking about the things that I really enjoy, which is force. So if you have questions, go ahead and throw them up in the chat. Otherwise, I kind of got everything somewhat organized for me so I can see what's going on. So force equals the mass of the objects times the acceleration that it's occurring, or that it is effectively undergoing. So right now, all of you guys are putting a certain amount of force into your chair, into the floor, into your bed, into your couch, whatever you happen to be. And that force is going to equal to the mass of your body, and specifically the acceleration or the accelerations that you happen to be encountering. So right now, we have the acceleration of gravity pulling us towards the center of the planet, and that in turn is what's giving us the force we're feeling into the ground. So if you don't have any gravity around you, you effectively have a mass, but you don't have any perception of force. Now, the thing is, as soon as you start moving, so as soon as you start standing up, you now not only have the acceleration of gravity pulling you in the center of the earth, but you also have the acceleration of you moving your body from 0 to whatever speed. So you're going to feel a greater amount of force. And if we had a scale on the ground, you would all of a sudden weigh more than what you currently do because you are producing more force. And then the opposite is true. As you sit down, you're actually producing less force into the ground than is required to maintain your body position. So if we want to know acceleration, all we have to do is figure out the force and divide that by mass. So just good old-fashioned algebra, guys. We're going to be going ahead and moving around through multiplication and division, our different units. That way we're going to get to the results we want. Now, if you are trying to figure out effectively how fast something's accelerating, well, if you knew how much an object weighs, let's say you have a bowling ball and it's sitting in the driver's seat of a car, the passenger seat of a car, and you have a scale behind it. Well, it's going to have a set amount of essential force that the bowling ball is naturally going to be kind of rolling back into it. Now, as soon as you try to accelerate the car, you're going to see that weight go up, and that's going to be the total force it's actually exerting on the scale. So if we know the force and we divide that by the mass of the object, is going to give us the acceleration that the object encountered. Now, the next concept we have is going to be what's known as momentum. Momentum is capital M, where it's going to be equal to the combination of our mass times our velocity. So the big key here is it's a quantity of an object in motion. Okay, inertia is whether or not you're moving or not moving. Momentum is when an object is moving. So this is the equivalent of when you're moving forward, you have a certain amount of momentum that is carrying you forward. And for those of you guys that are smaller humans, how many times have you had a larger human walk into you and they knocked you backwards? That's an example of their momentum is greater than your momentum. Or if you guys ever see any video online of a train hitting a car that's sitting on the tracks, whether it's a tractor trailer or a small sedan, that thing gets obliterated because the momentum, the mass of that train is huge, even without it having a great velocity. So now for those of you guys that ever played football, rugby, a sport where you actually had to tackle another human, a lot of you guys probably intuitively know this, which is if the other person outweighs you by a large degree, the only way that you can go ahead and effectively take them down is by literally going, in this case, if you're half their size, twice as fast as them just to stop them. Now, another key component, and the concept can be a little difficult to understand, which is what's known as impulse. Impulse is a change in momentum. So what we're really looking at is that change in force divided or multiplied by our change in time. So our impulse is going to be effectively the same in a lot of situations. So wherever you guys are, I want you guys to go ahead and stand up. Okay? So go ahead and stand up. Once you go ahead and do so, I want you to go ahead and just think, jump as high as you can into the air, and I want you to land as softly as possible. Okay, land as softly as possible. It's better if you're doing this barefoot because you're really going to feel effectively the amount of force you're absorbing into the ground, and hence the amount of impulse that we're totally getting. So if you really absorb, you really take and you squat down into that landing, you're letting your ankles, knees, and hips absorb the jump, you're going to have a set impulse from that jump height. Now, if you jump again as high as you can, only you land straight-legged or you barely absorb, you're going to feel a much greater amount of force because the period of time that we're absorbing that force over is much smaller. So hence, it's the exact same impulse. Does that make sense to you guys?
Yes.
Now, think about sport. If you know that something's going to hit you, meaning a opponent is going to collide with you, if you're doing MMA or boxing, someone's going to punch you, what can you do to effectively you have the same impulse, but what can we do to try to decrease the maximal amount of force?
Kind of like absorb the punch or go.
Exactly. Yeah, you're right, Zach. Think roll with it. Try to take the punch or take the hit into you if somebody's tackling you, rather than like, yeah, go ahead, just throw your shoulder in my hip as hard as you can. Of trying to roll with the blows, and that's going to allow for, once again, a smaller amount of force you're going to have to deal with. So here's another happy example. If we're going to talk about karate chopping a block or just going ahead and essentially pushing hard on it, turns out both are going to give the same amount of impulse. The key is the greater amount of force because the shorter amount of contact time. So what we really want to do is really have a longer amount of time to produce force in general if we're trying to throw an object as far as possible, if we're trying to accelerate ourselves at a higher rate, because we can obviously apply that force for longer. Now, obviously, it doesn't always work like this perfectly, but what you're going to naturally see is an overstride effect where people are going to get that leg in front of them if they're doing the high jump, and then they're also going to lean back as they're throwing that javelin so that they're going to have a greater amount of time to go ahead and throw the object with. Yeah. Now, we see the same situation whenever we start sprinting, in that we have a much longer or a much greater impulse because you've got a greater amount of contact time. But once we get up to high speed, it's really hard to apply much more force because we've got such a little period of time that our foot is actually in contact with the ground. Now, the same is going to be true, like we gave you guys with the jumping example, of if we happen to take a greater amount of time to absorb, we're going to not have to experience as high of amount of force. So it's really important when we're working with athletes or anyone that we're teaching them not just produce force maximally, but to know how to absorb force well. Can you guys think of another example of something someone can do to help with their ability to absorb force in a sporting movement?
When you shut off a block in football, from a defense perspective.
Oh, that's good, Zach. Good. What else, guys? Yeah, of bending the knees, bending the ankles, and bending the hips on landing from a jump. That's absolutely true, Luke. Think about throwing a pitch in baseball or softball. if you didn't let the athlete naturally follow through, you're going to put a much greater amount of force through the shoulder joint, because instead of going and then fully extending, letting themselves relax, if they just try to whip it and stop it immediately, that's going to put a huge amount of force on that rotator cuff. Now, another big component to think of when we're looking at force is going to be pressure, okay? Pressure is simply equal to the amount of force we're going to encounter divided by the area that we're doing this over. So we want to effectively use equipment or effectively methods to typically help us increase the area we're absorbing over. However, we quite frequently want to go ahead and decrease that amount of area that we're applying force whenever we're trying to effectively strike another object. So, for example, even the biggest person in this class, if anyone was to literally stand, literally just put their foot on top of that person's hand while their hand is on the ground, and as long as their hand's not sitting on top of like broken glass, you're going to be absolutely fine. But even the smallest person in the class, if we had them wearing golf spikes and had them step on that person's hand, because of it's the same amount of force, but notice the area is much smaller because of the wonderful effective metal cleats and otherwise, that's going to go straight through somebody's hand no matter how small anybody happens to be in this class. Does that make sense? Great point there, Luke. Absolutely. Those self-defense weapons are all about trying to use, I mean, let's face it, that's the reason why someone is punching you. Yeah, it hurts, but if they put the same amount of force, only it's the end of a knife blade, that knife goes into you quite a distance. Because yes, the pressure is going to be much greater because the area is so much smaller, even though the force is about the same. The other thing is with self-defense weapons, you're typically increasing the lever arm. So that's allowing you to produce a greater effective amount of force because we're able to get at a higher speed at the end of that lever arm. And the deacceleration when you hit somebody is going to be about the same. So not that I am saying that you should attack people with baseball bats, but that's the thing. Okay. Now, the next component we're going to talk about is what's known as work. And specifically, we're talking about mechanical work. And this is simply going to be the force applied multiplied by the distance it's doing this over. Okay? This is going to be the big key when we're looking at athletes and specifically things like weight training, which is if we know the amount of load that they have to move, so we can figure out the force because we've got the mass and we've got our wonderful acceleration of gravity. Remember, that's going to give us force. And then we can know the distance of how far they're going to move the object. Because the key is if you, so later on today, I'm going to be deadlifting. So when I pick the bar up, it's going to come X amount of distance off the ground. So I have a positive acceleration and then a negative acceleration, and then I let it go back down and repeat and repeat. And that is going to be equivalent amount of force. And then the distance is going to be that range of motion. And so if we then are going to multiply how many times I'm going to do those repetitions, we could literally figure out how much work I'm going to do. And that's going to give you essentially training volume. And training volume is important because that gives you an idea of literally how much stress you're really applying on that athlete. And sometimes we can give people too much volume than what they can recover from. Because it is work, literally, for you guys to carry your body over different distances. Now, work is great when we're just looking at total amount that someone's doing. But where you're winning and losing sports is going to be in your ability to produce power, okay? Power is going to be this work divided by time. That's it. So it's force times distance divided by our time. Now, here's the thing. Whenever someone does like a power clean or a snatch compared to a deadlift, not only do they have a greater distance, but typically a greater amount of power, because you cannot power clean or snatch slowly. You have to move the weight quickly. And if you don't move the weight quickly, you're not going to be successful with your repetition. Meanwhile, when it comes to something like the deadlift, you can move as slow as possible. So you can do it, but not be very powerful. Now, when we're looking at things like your vertical jump, that's going to be the force you applied over the distance where you had yourself on the ground, and that's going to then propel you up in the air, and we can figure out how much power you produce. So same is to be said when you're sprinting, when you're accelerating your body. It's the equivalent of, if I am to go ahead and take my teacup and walk all the way back to the back of the classroom and set it on the windowsill, or just pick it up and throw it and get it to nail the back window. Both are the same amount of work. The key is the second one was a lot more powerful. And when we're looking at cross-country athletes, the athlete that won is literally the athlete that produced the highest power relative to their body mass on average over the 5K. Does that make sense to you guys? Awesome. Now we're going to talk about forms of energy. Now, the first one is what's known as kinetic energy. And this is effectively the amount of work that's being done in order to get an object to move, okay? So kinetic energy is going to equal 1/2 of our mass times our velocity squared, okay? And this is going to give us a form of energy known as effectively joules. These are the same units that we get for work, okay? Now, the reason we care about kinetic energy is because we're going to be using this to convert back and forth on occasion into what's known as potential energy. And potential energy is stored energy. So anything that is sitting off of the ground, if we were to go ahead and let it fall, we're going to release that energy, okay? Now, the greater the height that that object is falling from, the greater it weighs, the greater amount of potential energy. So the formula for potential energy is going to equal our mass times the gravity it's experiencing multiplied by the height in meters that it happens to be off the ground. Now, a great example of converting from kinetic energy into potential energy is literally the vertical jump. So when you jump off the ground, so when you're leaving the ground, you're going to be at that peak velocity, okay? And you've got that 1/2 your mass times velocity squared. Now, as you jump up off the ground, at the top of your jump, you no longer have a velocity. So effectively, for a very small moment in time, you have no positive or negative velocity. Instead, all you have is your mass, the gravity you're experiencing, and the height you happen to be off the ground. And so then your potential energy converts back into 100% of that kinetic energy that you took to jump off the ground. So you hit the ground with as much potential energy or with as much kinetic energy as you took off from the ground. Does that make sense to you guys? Awesome. Thank you, guys. Now, here we have a happy example of both momentum and kinetic energy. So we have the real big lineman going at the real little, I guess that would be like the running back. And you see they have the equivalent amount of momentum, but notice the kinetic energy, the amount of work they have to do to get to those velocities are in fact different. Now, when they hit each other, they're going to cancel out the momentum and they're going to be at a dead stand or dead stop for both of them. And then on the other side, when we look at the bottom, you've got that same running back and now what would be like a free safety where same thing, same momentum, but notice the amount of kinetic energy required to get to those velocities are going to be much higher for the smaller individual. Now, the last type of energy that we're going to touch on is what's known as strain energy. And this is ability effectively to have rebound or recoil after something has been essentially modified a little bit. It's been stretched, it's been pulled, it's been compressed, it's been twisted, and then it's going to go back to its initial position. And strain energy is going to be equal to half the volume of the object multiplied by the stress and then multiplied by the strain. Okay? Or this can be one half of the volume multiplied by Young's modulus, which is a set component depending on what type of object we're talking about, and then the strain. Now, obviously, we've got a tennis racket example here. What part of your body can you guys think of where you're going to have a certain amount of strain energy? All right, so what I want you guys to go ahead and do, legs, yes. Yeah, it's going to be in a lot of different spots, but just a real quick, easy one is once you go ahead and put your hand on the table of wherever you're at, okay? Now from here, you're going to grab a finger, you're going to pull it back, and then just let it go. Notice it's going to snap itself down, especially when I pull it way back, because I am creating not just potential energy because I've lifted my finger off of the table, but strain energy because I'm putting a stretch on those tendons from my flexor digiti, along with putting a slight stretch on the muscle belly itself. So when I release, I get that energy return. Does that make sense to you guys? So Cassie, you're right, especially depending on your position. And I know from the fact that both Caitlin and Zach have been in yoga with me in the past, where you can, and you guys can go ahead and feel free to chime in if you'd like, but obviously there's a number of stretches that you can actually feel your body wanting to recoil out of those positions, especially whenever we had your partners helping you out, stretching in certain positions.
The back bend.
Yep. Yeah, we're winding up a lot of tight tissues there on you whenever we're doing that, Zach, and that's okay. So that's strain energy. So we've got kinetic energy. Remember, that's an object in motion. We've got potential energy, which is how far can it fall. And then we have strain energy of effectively pulling back tension on a line. I keep doing that because I think bow and arrow. Okay? So from there, aside from the bow and arrow, what are some examples that you guys can think of where you're going to have all three types of this energy at the same time?
Would running be one? Just
Yeah.
flat out running? Yeah.
Yeah, because A, you've got kinetic energy because you're moving. B, you've got potential energy because you can always fall. And then C, your actual tendons and muscles are going to have a slight amount of strain energy with each of those movements. You have always a certain amount of elasticity in your tendons and in your muscles themselves that's going to go ahead and effectively be pulled back to build tension and then release it as you're moving. Good. What other examples can you guys think of?
I thought about gymnastics, just in general gymnastics.
Okay, so now gymnastics, especially depending on what you're doing, Catherine, is a great one because think about it. Not only kinetic energy because the gymnast is moving, potential energy because obviously they're going to be jumping up in the air and somersaulting, but often or quite frequently, gymnasts are going to be on what's known as a spring floor. And that spring floor is going to be giving them a solid amount of strain energy, just like if you're jumping on a trampoline. And Braden just put up pole vault, which, yeah, because you're converting, that one's really cool because you're converting your kinetic energy into strain energy on your pole, which is then converting it into kinetic energy, throwing you up in the air, and then eventually all into potential energy when you're at the very top of your vault and then falling back down to where you hit the mat. with all of the kinetic energy you started with. And pole vaulters are crazy. They're fun to watch, but boy, howdy, they are crazy folks. So, great job there, guys. Now, the next component to understand that's obviously very useful in sport is what's known as rebound. And this is going to be when objects impact and separate, how much return do they get of the initial energy they had. So think of bouncing a basketball, okay? If I just drop the basketball, it's gonna bounce. Now that first bounce is probably not gonna be as high off the ground as I dropped it from, it's gonna be much lower. Now, objects that have no rebound, so an example of that would be like clay, so if you go ahead and drop it, it just hit and sticks. Other objects, like if you think about like the bouncy balls you used as a kid, it's gonna bounce and nearly give you almost a coefficient of restitution of 1, meaning it's going to have the same velocity that when it hits the ground with, it's going to return with. Now, when you're playing sports, it's not just the object you're playing with, but the surface you're playing on that's going to make some major effects on rebound. So when we're talking about rebound, guys, what type of sporting, give me an example of a sport where you've got really high amounts of rebound. Don't confuse this with basketball where you have to, rebounding is actually a skill and a statistic. Tennis can definitely be one. Now, tennis is fascinating because tennis is played actually over 3 different surfaces. There's hard, there's grass, and there's clay. Playing on the hard surface is actually the fastest one because that's where you get the greatest amount of rebound. When you're playing on clay, that is going to be the one that's going to be the softest, where you get the lowest amount of rebound, where the ball isn't going to bounce as much. And so different surfaces are going to give you slightly different ways that you're going to play the sport. And that's why you see some athletes are really successful on a hard surface and others are really successful on a soft surface. Good job. All right. When you say football, Catherine, go ahead and give me an example of it. You're always going to have a certain amount of force because the equal and opposite reaction whenever you punch something or otherwise with boxing, but the surface isn't going to make a big difference. You are on the ring, and the ring doesn't let you bounce that much. Okay. A dig in volleyball. Okay. So yeah, you're going to maybe bounce a little bit off the hardwood, but if you're doing that on sand, you're not going to get a whole lot of rebound. Once again, guys, think about objects bouncing. That's the big key. Yes, but that's also going to be an example of getting where we talked about kinetic energy and we talk about momentum. Now, okay. So let's go ahead. And I'm going to try to pick on Caitlin, but we'll see if she's maybe away from keyboard. Oh, good. Because that's where I was going to try to take it, Raylan, cheerleading. Absolutely. Depending on the surface you're going to be jumping off of or landing on, let me tell you, you're not going to really bounce that much whenever you hit those objects. And specifically, that's why it tends to be try to be on a softer mat where you're going to have that little bit of rebound. Whereas if you just hit and smack, that's really, really uncomfortable. And that's the gentlest way to go ahead and define that. So with rebound, guys, we're effectively talking about our return on our kinetic energy. And this is what's fascinating because literally this is what's going to not just give us the velocity, but it's literally going to warm the object up because of the friction between the surfaces. We're going to get to friction in a little bit. So what's interesting is some sports literally try to effectively take not necessarily advantage, but make sure that they try to homogenize by literally making the ball warm enough to play with. Sometimes it's going to be things like the temperature of the hockey puck you're playing with or the football, which is actually going to influence how it's going to bounce and how it's going to play. Aside from, slightly deflating it because you're playing for the Patriots, but that's a different story entirely, allegedly. Now, the angle of which we're going to go ahead and bounce off the ground with, along with the velocity, are going to influence its rebound. Now, spin is important because any of you guys that ever played baseball, softball before know that when the ball has a great amount of spin, it hits the ground, or ping pong is a really great example, is you're gonna see the ball shoot off in a random direction because of the spin that it happens to have when it hits the ground. And then the friction essentially between the two surfaces is in turn going to influence its ability to go ahead and bounce, because if literally the friction's high enough, it's going to cause it to stick and it's going to have a much greater loss of that velocity. So I'm sure all of you guys at one point or another have seen a ball curving in the air in flight, and that's going to be literally caused by the spin that has been applied to it. And so the greater amount of spin that happens to be on the ball, the greater amount of rotation and movement you're going to see in the direction, effectively due to what's known as the Magnus effect, which we're going to get into at the very end of the class. But just understanding this is going to influence projectile motion. Now, friction is going to be effectively the amount of force that we're going to have between two surfaces when they are touching each other. Okay? So higher amounts of friction is going to be caused by the coefficient of friction, and that's going to be a set number when we have two surfaces up against each other. And the normal perpendicular force is literally the amount of force going into the two surfaces. So right now, there is a coefficient of friction between my feet and the ground. So I'm wearing shoes with rubberized soles, and I'm standing on linoleum with a layer of wax on top of it. So due to the coefficient of friction between the two of these, I have pretty good grip on this surface. And the normal perpendicular force is literally the force of my body going straight into the floor. Now, if I am to go ahead and lean and be off to the side, I still have a certain amount of my force that's going straight down, but now a certain amount of my force is going backwards. And if I keep going and lowering my angle, eventually I'm going to hit a point where my normal perpendicular force is so small that eventually it's going to cause my feet to start to slide. So this is an example of when we talk about the normal perpendicular force. So a sled is going to have a set coefficient of friction, but the normal perpendicular force is literally just the center of mass on the sled going straight down into the surface the sled's on, so the ground. Then we can increase the normal perpendicular force by putting what looks like a child followed by their happy dog on top of it. So notice the normal force between the bottom of the sled and the ground is increasing. You can see the size of the arrow specifically from the bottom increasing because of the greater amount of force that it happens to be encountering. Now, depending on how we push an object is going to in turn influence how much force it's going to encounter. So if I am to go ahead and push this table I'm talking to you guys from forwards, I'm not only using a force vector pushing it forward, but I'm also using a force vector pushing it downwards. So I'm literally creating a greater amount of friction, making it harder to move the object. Whereas if I am to grab and pull the table towards me, I'm making the table a little bit lighter. At the same time, I'm pulling it back in towards me. And that in turn is going to give me a lower amount of force I need to produce in order to overcome the friction. Now, friction is going to come in a variety of forms. Static is just going to be when two objects are not moving on one another, so they're just in place. Sliding, or what's known as kinetic friction, is going to be whenever one object is sliding across another. And then we have rolling friction, which is going to be the resistance to literally rolling a round object over a surface. So we're going to find that the amount of force needed to overcome that static force or static friction is higher than the amount of force needed to keep it moving. Dynamic friction is essentially always going to be lower than static friction. So you can see in this box example, box is going down to the surface, then something is going to go ahead and lean on the box. It has not yet overcome the static friction, so it's still holding its position. And then once it does overcome it, the box is going to start moving, and then immediately we're no longer with static friction, we're with dynamic friction, which is a smaller number, so that's going to allow that box to go ahead and move. So if we're going to actually look at a time of the amount of force being applied and then the amount of frictional force, you're going to see we're going to go all the way up until the static friction is overcome by the external force, and then boom, the amount of friction goes down because now we're over into dynamic and the object is going to be moving on the ground. This is, if you guys ever do really heavy sled drags or pushing cars, if any of you guys ever want to join me pushing cars sometimes or something like that, I enjoy it. Maybe I was a sled dog or a draft animal in a previous life, I don't know. But A, it teaches a lot about friction, both rolling and otherwise, and B, it gives you a lot of good work. And C, I don't know, we can maybe talk about our feelings or something. You guys let me know, but we will be wearing masks. Now, when you're looking at, say, an example of a horse pulling a cart, okay? The horse has to have a greater amount of friction force between its hooves and the ground, so hopefully static because it's not sliding, than the friction between the wheels of the cart, and that's going to be rolling friction. When it's doing so, it's going to be able to move it forward. If it's not able to, then the object's going to be stuck in space. And that rolling friction effectively is going to be the combination of coefficient of friction, the normal perpendicular force of pulling it down into it, and then the diameter of the wheel or the ball. So if we have a smaller diameter compared to a greater diameter, that in turn is going to literally change our ability to get to effectively move that object. So if you're trying to increase your friction between the tires and the road itself, obviously better tread, lower tire pressure gives you a greater amount of tire that's actually touching the ground. Adding chains, gravel, salt, all of that's going to roughen the surface to make it a little bit better. Along with, we can add weight to the car, which can increase the normal perpendicular force. And the funny thing is, if we actually use smaller tires, it's actually going to go ahead and allow us to increase that rolling friction. It's the larger wheels that actually have the lower amount of rolling friction to them. So if we want to go ahead and have the opposite effect, we're literally going to do the opposite side, which if you decrease rolling friction, it does make the car drive a little bit more efficiently. However, it is going to make it a lot easier for you to slide and for you to lose control of the car when you're driving it. And let's face it, another thing that we can do is rain or, of course, put some ice on the ground. So that is our joys of talking our way through all of chapter 3. I realize when I'm just talking to myself, things tend to move a lot faster, which is not necessarily a great thing. However, we now, fortunately, understand even more of this math than we did previously. So now what we're going to go ahead and do is we're going to go ahead and have a little bit of fun with numbers and hopefully science. So let's go ahead and, well, actually, first I want to kind of illustrate the wonderful effects of static compared to dynamic friction, okay? And this is, and we'll even talk a little bit about the wonders of potential energy. So what I have here is a notebook. We've got the cardboard side and we've got the glossy side. I then have a pen. So if I go ahead and put our happy pen on top of our notebook, right now it has the normal force going into the surface. And however, as I start to lean the pen, now notice it starts to shift, and then eventually it slides off. That's because as I tilt the surface, what we're going to see is a certain amount of the force is still going directly into the surface. So when it's in an angle like this, the normal force is going directly in. However, the other force vector is pulling it down. And as that number increases, once it overcomes the coefficient of friction, you saw it, once it starts sliding, it doesn't stop. So if we switch over to the other side, and now we're on the I guess, arguably rougher side, we're going to see that I can tilt, 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 and it can stay a little bit longer, but then rut-row, because once we overcome that static friction, it's going to go ahead and keep on moving. Does that make sense, guys? Trying to illustrate it. Now, mathematically, how we'd set that up is going to be a bit different. So what we're going to find is if we were to draw this out, we're going to go ahead and see we've got this object where the force is pulling it straight down, but that naturally creates two force vectors, one into the surface and one that happens to be perpendicular and one that's parallel to the surface. And all we're looking for is, remember, our total friction force that we need to overcome is going to be equivalent to our coefficient of friction multiplied by our normal force. So once we go ahead and overcome that value, we're going to go ahead and find that object is going to be sliding on down. Yeah, no worries. So remember with levers, guys, we're going to have a first class lever, which is that good old seesaw. Our second class lever is going to go ahead and be where we have the fulcrum on one side, the resistance pulling down somewhere in between, and then our actual lifting force is going to be on the end. So think wheelbarrow. And then finally, we're going to have our third class lever, where we're going to have the fulcrum on one end. We're going to have our force lifting up somewhere in the middle, and then we're going to have a resistance at the end. So this would be the equivalent of using something like a fishing pole, which is going to be how things like our biceps are working whenever we happen to be lifting an object. So let's go ahead and have a little bit of fun with math. So notice, guys, now after everything we've talked through today, we are able to go ahead and look at effectively a lot more of this wonderful cheat sheet you guys should have making sense. So we've talked about kinetic energy, potential energy, strain, pressure, work, momentum, friction. I guess I put work on there twice, which is kind of funny now that I'm seeing this. And remember, the work here is going to be M is meters. We've got power, we have impulse, and we have momentum and coefficient of restitution. So really, every single one of these, you guys should now know. Go ahead and delete. Okay. Now, let's go ahead and we're going to start off with a way that we can go ahead and convert from kinetic energy back into potential energy. So remember my jumping example. Now, the amount of kinetic energy you have to create is going to be equal to your potential energy at the top of the jump. So what I want you guys to go ahead and do is I want you to figure out using your own body mass. So remember, your weight in pounds divided by 2.2 is going to give us your mass. Gravity for everything we're going to be doing in this class is going to be 9.81. And the height you guys are going to have for this one is going to be, we're going to make it leap like a freak. So we're going to say a total of 2 meters off the ground. So in order for you to jump 2 meters off the ground, how fast do you have to be leaving the ground at? In order to jump 2 meters off the ground, how fast do you have to leave the ground going? And you guys can throw the answer up in the chat. And you can always say, I have no idea what's going on. Will you please help me? That is always an option. Because remember, guys, you're here to learn. Okay, that's all right, guys. So remember, we're going to start off pretty easy with this. I've already mentioned it before, but honestly, a lot of this is new to you guys, so it's okay to be a little confused. So we're looking at kinetic energy and potential energy. And remember, guys, our kinetic energy when we leave the ground is going to be equal to our potential energy at the top of our jump. Because remember, we're converting from one to the other as we go. So if we're going to jump 2 meters off the ground, okay, we have kinetic energy, which equals 1/2 of the mass times the velocity squared equals our mass times gravity times our height. Okay? Now, the cool thing is, before we even start to put in values, this is on a really small screen, so you guys probably want me to go back to just putting my video up so you guys can see what's going on, right?
Yes, please.
All right, let's do that. So, our kinetic energy equals our potential energy. So the amount of kinetic energy we have when we're literally just starting to jump off the ground is going to be the same as our potential energy when we're at the top of our jump. So mathematically, kinetic energy equals 1/2 of our mass times our velocity squared, which is going to be equal to the potential energy at the top of the jump, which is going to be our mass times gravity times our height. And so first thing we can do is we have mass on both sides. So think old school algebra, we cancel out our masses. So now we have 1/2 velocity squared equals gravity times height. Okay? Now, let's think about what those values were. Gravity is 9.81. So we have 9.81 times, and how high did I say we're going to jump in the air, guys?
2 meters.
2 meters. So 9.81 times 2 equals velocity squared. So from here, we're going to go ahead and do the square root. So we're left with a final formula of velocity equals the square root of 9.81 times 2. And that's how fast you would have to jump off the ground in order to leap 2 meters up into the air. It's like 4.4 something. Oh, dear God. Thank you, Corey. I screwed up, buddy. You're right. We have the 1/2 of the velocity, so we forgot to multiply this by 2 again. He's absolutely correct. I forgot to pull that side on through. So we have to multiply this also by 2. It would be 4.429 if I set it up correctly, but I didn't. So what we actually just solved for there, Luke, which you did correctly, would be if we were only going to jump 1 meter into the air, because I forgot to move the 1/2 velocity. But thank you for finding that, Corey. So our answer is probably going to be 6.3 something? Square root of 39.24. Nice. 6.26. Good. Is that what everybody else is coming up with? Awesome. So from there, you're done. Questions there, guys? Okay. Good. So let's go ahead and let's try another one. Okay. If we go ahead and we're going to do a work formula. Okay. Now, guys, remember force, okay, equals mass times acceleration. Okay. And the units for force is going to be what's known as newtons. Okay. Work equals our force times the distance we're going to have moved. So the displacement. Now, if let's say you guys are going to go to the rec center and you're going to go deadlift 100 kilograms. Okay. So you're going to lift 100 kilograms and you're going to do 3 sets of 10 reps. And each of those reps, you're going to move the bar 1 meter. How much work are you going to have done? Remember, you need to figure out force in newtons. It's not just going to be in kilograms. 29.42. Okay, so the key is you're going to have done 3 sets of 10 reps, which means you're going to have done 30 total repetitions, and each of those repetitions is going to move you 1 meter. So you're actually going to have your distance total is going to be 30 meters. Okay? It's okay. It's okay. The thing that a lot of people are going to mess up on this one straight up is they're not going to figure out the force. Whenever you guys think you have the answer, go ahead and put it up in the chat. Okay. Haley's looks pretty close. Anyone else agree with her? All right. So, Haley, how were you able to figure out the amount of force you had to produce to lift that barbell?
I didn't know how, so I went online and did a converter. I don't know how to actually do it.
Okay, that's all right. That's all right. So your mass is going to be 100, and then you're going to multiply that by the acceleration of gravity, which is going to be 9.81. So that means our force is going to be equal to 981, and then we're going to multiply that by our total distance, which is going to be 30, and that's going to give us our work. Does that make sense? Good, Luke, good. Guys, we're going to do as many of these examples as you guys want to do. It's fine. 100% transparency here. It feels really freaking weird doing these because I don't know what you guys are doing over there. So it's just me standing in a room by myself, and I don't know whether or not I'm going too slowly or if I'm going too quickly. All I know is I feel really awkward. So hence, throw up in the chat if you're struggling, throw up what you guys think is or what you guys think the answer is, because it's okay to make mistakes. I will go ahead and help you guys figure out hopefully where you made it and then go from there. Okay, so we've got that answer of 29420.0. If we're going to go ahead, and that's the total amount of work we did. Now, if we want to figure out the power we were producing when we did it, what do we need to do?
You have to divide that by the time, correct?
Exactly, John. So from there, if we wanted to figure out what your wattage was, well, let's figure out the amount of time it took you to do it. So if I told you guys you had to do 3 sets of 10 on the deadlift on a weight that's somewhat challenging for you, but isn't going to have you meeting your ancestors somewhere along the lines, about how many seconds do you think it would take you to do all that work? You guys can just throw a guess.
Probably like a 10 to 15-second range, maybe.
For each set or for all 30 reps?
Oh, for each set. I was gonna say for reps.
Yeah. Yeah. So I mean, you could probably bust out one a second. So from there, actually maybe even faster depending on how strong you are. But from all we would do is literally, in order to get our power, we would then take that 200 or 29,420.1 and divide that by 30 seconds, and that's going to give us our power. Now, remember, work is in joules, and then the most jacked up thing is power is in watts. Love it when it's named after dead white guys, because it can make it a little confusing for you guys. So power, the unit for them is watts, capital W. Work, the units for that is joules. But all you have to do there is take that 29420.1 and divide it by 30 seconds, and boom, you've got your power. All right. So now, okay, by no means do we need to figure out your exact body weight, but just, ballpark your body weight. Let's see here. Okay, you know what? We'll have some fun. We're going to have it all like this weird type of, you have to knock me, you have to stop me from knocking you over, okay? I'm not fast. But we're going to go ahead and assume, because we're going to do a momentum problem. And so your momentum has to equal mine. Remember, capital M equals mass times velocity, okay? I weigh about 95 kilograms, and we're going to say my top speed is slow, but I'm going to use the power of the Googles to convert, because I'm not great at converting from miles per hour into meters per second. So we're going to say my top speed, we're going to say is, I don't know, we'll say, 20 miles per hour, because why not? No, that's probably not possible. Let's go with 16. And I'm still probably being way too generous. And so that gives me a grand total of 7.15264 meters per second. Now, so this is M2, you're going to be M1. So if I'm going as fast as I can run, okay, then you're trying to come at me at the speed you need to in order to stop me. How fast do you need to be running? So you're going to take your own body weight, and we're converting that into kilos, and that's just going to be your weight in pounds divided by 2.2. And from there, so you're going to have your mass multiplied by your velocity. And so you should be able to figure out your mass. So you're going to divide both sides by your mass. So then you're going to be left with the velocity that you need to be going in order to stop me at a full sprint. Do I have another marker? I will go get one, because, oh dear God, yeah, you can't see that to save your lives. I'll be right back, guys. Science if you want. I got it, coach. Is that better, guys? Awesome. So now, this will be the last thing we do. How fast you got to be going to stop me? And whenever you guys think you have a solution, just go ahead and put that up in the chat. Nice. Yeah. Seeing as how a lot of you guys, some of you I have met in person recently, a number of you guys I haven't, so hence the body mass thing becomes a real big question mark. And the key is, if you weigh more than me, you don't have to be going as fast as I am. If you are smaller than me, you got to be going faster. And especially if you are a very small person mass-wise, then you've got to be going a whole lot faster to be able to stop me. Yeah, so there we go. Haley, you are obviously markedly smaller than I am. So go figure. And then I think Zach's pretty close to my body weight, so his should be pretty close. And I know Raekwon is much larger than I am, so he shouldn't have to go anywhere near as fast. Anybody else got an answer yet? Make sure my ear hair and neck hair isn't in the way of the things you guys are trying to see.
You said we put our weight in the bottom of that.
Yeah, you should put your weight right there.
So just put those numbers in and just add our weight into it.
So it'd be 95 times the 7.15264 divided by your weight in kilograms, remember?
Oh, yeah.
That's going to give you the velocity that you'd need to be going. And so as you guys are still kind of wrapping up, yep, there we go. Like I figured, no offense, Raquan's a bit bigger than I am, so he's just not gonna have to be going as fast. Now, my last kind of for fun thing, and I'm literally gonna kick you guys out in a few moments so you guys can get on with your life, but I just think it's kind of a fun thought exercise, okay? You again are going to be running, okay? And this is a thought exercise. I don't want you to do it, okay? Just so we're 100% clear on this. You've got your mass, which you guys know, and we're gonna say you're gonna be running at a nice, even, let's go with 6 meters per second, there is an entire school worth of toddlers coming at you trying to stop you. If each toddler weighs 20 kilograms and they're waddling towards you at 1 meter per hour, how many toddlers would it take to stop you? And Cassandra has a great question about lab 1. So give me a second and I will pull up the lab and we will talk through it so you guys know. There, if you go on YouTube, there's just like a simple example of me going through the lab. So you guys can go ahead and use that for what you guys are going to have to do. But specifically for lab 1, which is meant to be done with what's known as a goniometer. And give me a second. Okay, so this is the one that is going to be due this week, and this is what I want you guys to be working on, and you're going to do your best to do this obviously from home, okay? So you're going to be measuring these different movements. So internal rotation is going to be going in out as far as you can. External rotation is going back as far as you can. Shoulder flexion is going to be going behind you. Shoulder extension is going to be going overhead. And then hip internal rotation is going to be where you're going to rotate your hip inwards. Sorry, leg into the middle. And then, I'll just make it weird. Internal rotation, external rotation, and you're measuring how far you guys can go with those. You can just use a camera on your phone otherwise, and you're going to measure those degrees to the best of your ability. Hip flexion is going to be lifting that leg up as high as you can in front of you. Hip extension is going to be bringing that foot behind you. And then you're going to look at the exercise for your group project. So you're going to pick the same joint for all of those movements. The preparation phase is getting set. So let's say you're talking about someone throwing a baseball, and we're going to look at the elbow, the shoulder angle, and everything when they're started here. The wind up is going to be that going ahead and coming back, and well, as I run into the wall, and then what are the angles and everything here. Then, and you can even be all the way back in the throw. The force producing is going to be coming through and forward. So what are the changes and angles you're doing there? And then the follow through is going to be the end of the movement. So you're just going to try to figure out how many degrees you move through each of these segments. So bench press is easy because we could look at where the arms are at the top of the movement. So our preparation, we then have our wind up where we're bringing it down. So we have the angle at the shoulder and at the elbow. We have our force producing where we're going to come back up. And then we're going to go ahead and have our lockout to let go of it. And we're looking at the angles at each of those. So take your time, working your way through it. And everybody feel pretty good about that now? I'll take that as a definite maybe. So you should be able to find like goniometer apps that you can download for free. And that's going to allow you to do those same type of degree measurements. But when in doubt, you can always just take the video and think, if you start here and you end here, how many degrees do you do? And my shoulders are garbage. Like that's it. It hurts. The joys of heavy lifting. So you guys have a great day. Stay safe out there. Get yourself on to your next classes. And I will see you back in here on Tuesday morning. Bye-bye, guys.